it's me, Ma'am Ed.
Well, there's a lot of science stuff. Come on, let's explain.
Have you ever wondered why different elements emit different colors of lights? That's the mystery we'll solve today using the Bohr model of atom. We will explore the challenges that lead to Bohr model, learn how energy quantizations, explain atomic stability and emission spectra, and even calculate wavelength of emitted photons. Let's get started! Niels Bohr was dealing with some problems that were arising with structures of an atom. If an atom has a positively charged photons and negatively charged electron, why atoms are stable? Why don't the electrons just collide with nucleus? What are emission spectra? And why do different elements emit light of different colors? Bohr model of hydrogen atom addressed the several questions. He extended the idea of energy quantizations and said that the potential energy of an electron in a hydrogen atom is also quantized. This means that electrons can only occupy specific energy levels that fix distance from the nucleus. For hydrogen atoms, the energy levels depends on the Rydberg constants and are given by the following equations. And the Rydberg formula is used to calculate the energy change during an electron transition between energy levels in a hydrogen atom. Delta E, which represent energy change, is equal to negative R sub H times 1 over N final squared minus 1 over N initial squared, where the negative R sub H is the Rydberg constants for hydrogen. It is approximately 2.179 times 10 raised to negative 18 joules. And NF is the N final, where the electron ends, and also the Ni is N initial, where the electrons begins. Using this equation, we can predict the wavelengths of the photon associated with any possible transition for the hydrogen atom. Let's try this sample problem in transition from 4 to 2. Let's do it step by step so that you can understand it clearly. In this specific example, the electron transition from N initial is equal to 4 to N final is equal to 2. Let's now calculate the energy change. So let's use this formula. The negative sign indicates that the energy is emitted during this transition. Let's first substitute these values in the Rydberg constants into the formula. So energy change is equal to negative R sub H times 1 over 2 squared, which is the N final, minus 1 over 4 squared, which is the N initial. So it is equal to negative 2.179 times 10 raised to negative 18 joules times 1 over 4 minus 1 over 16 is equal to negative 2.179 times 10 raised to negative 18 joules times 0.25 minus 0.0625, because 1 over 4 is equal to 0.25 and 1 over 16 is equal to 0.0625. And the rest will be mathematics. So energy change is equal to negative 4.09 times 10 raised to negative 19 joules. Let's now calculate the wavelength. So the energy of the photon, or the E photon, is related to its frequency and wavelength. Solving wavelengths, we will use this formula. So wavelength is equal to Planck constants times the speed of the light divided by the energy of the photon. Where H is the Planck constants, it is approximately 6.626 times 10 raised to negative 34 joules seconds. C is the speed of the light. It is approximately 3.00 times 10 raised to 8 meter per second. And E photon is the energy of the photon, which is 4.09 times 10 raised to negative 19 joules from the step 1. Substituting the values, we can get this. So the wavelength of the photon emitted during the electron transition from N is equal to 4 to N is equal to 2, and the hydrogen atom is 4.86 times 10 raised to negative 7 M. So that is the final answer. The transition was grouped according to energy levels they land on. All ones that end on the N is equal to 1 are called the Lyman series, and the ones that end on the N is equal to 2 are the Balmer series, and so forth. Notice that this energy level gaps decreases as n is increases, and n equals infinity is actual infinite distance from nucleus. So if an electron goes beyond, it is considered to have been ejected from the atom. As we said, these energy are unique to hydrogen. Every element will have its own emission spectrum because every element has a unique nucleus and therefore differently spaced every levels. In this way, an element's emission spectrum is a sort of like a fingerprint unique to that element. This is how we can know the comparison of object in the space by analyzing the light that we see.
That concludes our lesson about Bohr model. Remember, each element has a unique spectral fingerprint, allowing us to analyze the composition of stars and galaxies. Hope you learned something. Bye-bye!